Hello everyone, welcome to this new video. So in the previous video we had discussed one concept related to electric field intensity, right? So in that concept you have seen the electric field due to several point charges and single charge, and we have discussed two important problems related to that. So those who have not seen that video, please go and watch it. It is available in this playlist only, because those videos, if you know, then only you could be able to understand the upcoming concept related to flux density and all. That is electric flux density. That is after this video I'm going to discuss. So in this video we are going to discuss about charge distributions. Okay, how the charges are distributed in different charge densities. Okay. Before going to the concept of flux density, we should be knowing these concepts very clearly. Okay, that is about charge distributions. So in this we are having three important kinds of charge distributions. This is related to where the charges are distributed linearly, or it is called as linear charge density, or the charges are distributed surface in the surface, that is surface charge density, and one more is final is volume charge density. Okay, so let us see what are these linear charge density, surface as well as volume charge densities. So first is linear charge density. So what is this linear charge density? Let us see. When a charge is distributed along a linear element, that is charge per unit length, that is called as linear charge density. Okay, so this is basically a one-dimensional surface where, for example, in a straight line, this is a straight line or a line segment where in this we are distributing the charges linearly in that particular line itself. Okay, so this is a one-dimensional line. So basically these linear charge densities are one-dimensional in nature. So that's why we should be finding the linear charge density whenever they mention. For that we have one particular set of formula, that is rho L. That is this is mentioned as linear charge density. So this is given by the formula rho L is equal to limit tending from delta L, that is delta L is the change in length. Okay, change in length which is tending to 0, that is into delta Q by delta L into coulombs per meter. Okay, so this is the formula for linear charge density, where delta Q is the charge in linear element. Okay, the change in charge in linear element which is given in terms of coulombs, and delta L is the change in length which is given in meters. Okay, so this was about linear charge density. Okay, it is basically a one-dimensional surface. Next we have surface charge density, or this is a two-dimensional surface where a charge is distributed along a surface element. The charge per unit surface is called as the surface charge density. You can consider this as one single circle here. In the circle it is distributed along the surface. Okay, the charges plus or minus, it's left to you, the charges or the ions are distributed along the surface. Okay, so this is the surface charge density. The charge per unit surface is called as the surface charge density. Okay, it is given in terms of rho S. Okay, that is equal to limit delta S tending to 0, that is the change in surface tending to 0, delta Q by delta S into delta Q by delta S, and the unit is coulombs per meter square. Okay, the delta Q is the surface charge, it is given in terms of coulomb, and delta S is the surface area meter square. Okay, since it is area, so that's why it is termed as meter square. So this is regarding surface charge density. Next we have volume charge density. This is a three-dimensional surface. Okay, for example, if you take an example of a simple cube or a cuboid. Okay, where it is a three-dimensional surface. In this you could take a particular box as an example. Okay, a particular box or something like that you could take. Inside there are filled with the charges. Okay, so this is the volume charge density. When a charge is combined within a volume, the charge per unit volume is called as volume charge density. Okay, it is given by rho V is equal to limit delta V tending to 0, delta Q by delta V, and the unit is coulombs per meter cube. Okay, meter cube is for volume, surface volume. Okay, yeah. So again these are the definitions of linear charge, surface charge and volume charge densities. Along with the formulas I've given it down, so if you want you can take it down. Okay, yeah. So regarding this, we are having some of the problems here. Let us see that. Before that, one note: total charge within a volume is obtained by integrating rho v, that is the volume charge rho v, over the volume. Okay, so total charge within the volume. So it is given by one formula, that is Q is equal to triple integration. Since it is volume, so we should be integrating 3 times with respect to x, y as well as z, because it is a 3-dimensional surface. So triple integration Q is equal to triple integration of rho v into dv, where dv is equal to dx, dy, dz, since it is a 3-dimensional surface. Okay, so according with this formula, let us solve some problems here. Let us see some problems. So first problem is, find the total charge in the volume defined by, these are the given definitions of x, y and z, that is that are the limits here. Okay, that is x is tending from 0 to 1, y is tending from 0 to 1, and z is tending from 0 to 1. Okay, that is x lies between 0 to 1, y and z also lies between 0 to 1. If rho v, they have given it as 40 x square y into 10 to the power 6 coulomb per meter cube, we should be finding the total charge, that is Q. Okay, so again same, they use the same formula which I have told you, that is Q is equal to triple integration of rho v dv. Since it is a 3-dimensional plane, so we are using with respect to x, y and z, where dv is equal to dx, dy, dz. I have told you already. So Q is equal to, first write the limits, okay, for all the x, y and z, that is 0 to 1, 0 to 1, 0 to 1, and the rho v value is 40x square y into 10 to the power minus 6 dx, dy, dz. So 40 into 10 to the power minus 6, you take it constant outside, so integrate 1 by 1, that is 1 dz, then limits are from 0 to 1 for z here, then into 0 to 1 limit y dy. Okay, why it is y, because here we have y term, it is multiplied by dy, so y dy, then we have x square dz, x square dx. Okay, so 0 to 1 x square dx. So integrate with respect to dz, it is z only, the limits are from 0 to 1, and y dy, the integration of y is y square by 2 with the limit 0 to 1, and integration of x square is x cube by 3 with the limits 0 to 1. Okay, upper limit minus lower limit, that is 1 minus 0, that is here we have y square by 2, upper limit is 1, so substitute that, 1 square by 2, that is 1 by 2, minus 0 by 2, that is 0, so we got 1 by 2 minus 0, into 1 cube by 3, that is 1 by 3 minus 0. 1 minus 0 is 1, 1 by 2 minus 0 is 1 by 2, 1 by 3 minus 0 is 1 by 3. So 2 3s are 6, so we are left with 1 by 6 here. So 40 divided by 6 is 6.67 into 10 to the power minus 6 coulomb. Our 10 to the power minus 6 is written as micro. So our final answer is the total charge is equal to 6.67 micro coulomb. Okay, yeah. So this was one simple problem where this is in terms of the rectangular coordinates, that is x, y, z. Okay, but sometimes they won't be mentioning only the rectangular coordinates x, y, z. They would be mentioning with the other coordinates, that is cylindrical coordinates or spherical coordinates. Okay, so what are those rectangular, cylindrical and spherical coordinates, that we are going to see in the upcoming modules. Okay, where we have a certain set of values for the volume, that is dv, which varies for these 3 coordinates. Okay, this was for simple rectangular coordinates, that is x, y, z. So we have one more problem here, second problem, where we are going to see in terms of cylindrical coordinates. Okay, yeah. In this is the total charge of within the volume of a cylinder. Okay, that was the total charge within the volume of a square type, or that is a cuboid. This is for the cylinder. Okay, calculate the total charge within the volume integrated by some of the limitations they are given for rho. This is rho, that is tending from 0 to 0.1. This is phi, tending from 0 to 5, and z is tending from 2 to 4. Okay, where the volume of rho v is given by rho square z square sine 0.65 coulombs per meter cube. Okay, so here in this case the value of dv, I told you that it varies for different coordinate systems. So in this case, the value for dV is given by rho d rho d phi dz. Okay, so here we are having one extra term rho. Okay, so this is for cylindrical coordinate system. Okay, keep it in mind. So here I have substituted that only here, rho d phi dz, where the limits are for rho phi z are given as 0 to 0.1, 0 to pi, and 2 to 4. Okay, yeah. First, for rho square into rho is rho cube d rho, with the limits from 0 to 0.1, into 0 to pi is for phi. So what we have here, sine 0.65 d phi, and for z it is from 2 to 4, that is z square dz. Okay, so integration of rho cube is rho to the power 4 by 4 with the limit 0 to 0.1, and the integration of sine is minus cos, so minus cos 0.65, where the coefficient of phi is 0.6, that would be getting divided, and the limits are from 0 to pi, and z square it is z cube by 3, the limits are 2 to 4. Okay, upper limit minus lower limit, so lower limit is for 0 itself, so that I am not considering here. Consider only the upper limit part, 0.1 to the power 4 divided by 4, okay, into cos 0.6 pi, the limit, the upper limit is pi, divided by 0.6, minus the lower limit is 0, that is again minus of cos 0 divided by 0.6, into 4 cube divided by 3 minus 2 cube divided by 3. Okay, so 0.1 to the power 4 is actually 0.0001. Okay, so that is written as 1 into 10 to the power minus 4 here, divided by 4, and here it is cos 0.6 pi. If you put it in the calculator, you would be getting minus 0.994 divided by 0.6 plus 1 divided by 0.6. Okay, here we have 4 cube is 64 divided by 3, and 2 cube is 8 by 3. Okay, so denominators are common, 1 minus 0.994, the answer is 0.006, or we could be writing it as 6 into 10 to the power minus 3. Okay, here we have 10 to the power minus 4 by 4 divided by 0.6, and 64 minus 8 is 52 by 3. Okay, and solve this here. After solving this, you would be getting 4 into 0.6 into 3, that is equal to 7.2, and here we have 10 to the power minus 4 and minus 3 is my 10 to the power minus 7. 52 into 6 is 312. Okay, after solving this, we would be getting our answer as Q is equal to 312 divided by 7.2, that is 43.33 into 10 to the power minus 7. If you want to write in terms of micro, so what we could be doing is we could be writing simply 4.33 micro coulomb. Okay, so this is our final answer of charge Q, that is 4.33. So hope it is clear. I've solved, we have discussed two of the very important problems in this topic of charge distributions in different coordinate systems and different type of charge densities as well, linear, surface and volume. So please watch this video till the end, and one problem related to this is fixed. Okay, one problem they would be definitely asking for internals as well as for external exams. So those who are having the internals, so it would be very beneficial for them, these kind of videos. Also the videos related to module 2, 3, 4, 5, all of them are available in this playlist only. So please go through it and like, share, subscribe to our channel. Comment your precious opinion about how you would be liking these kind of videos. Is it useful or not? You should be mentioning to us. Okay, yeah. So that's all guys. Thank you. We'll see you in the next video.